Hi team, welcome to Wiggins Maths. In this video we're going to be looking into the wonderful world of parametric equations. Okay, this video focuses on changing a parametric equation into Cartesian form, and these examples contain algebraic, exponential and logarithmic terms and does not focus on trigonometric functions. Okay, firstly, what is a parametric? Well, firstly, let's have a look at what we do know. We know functions like this. This is called a Cartesian function, named after the mathematician and philosopher René Descartes, where x is the input and y is the output of this function, and we can plot these on a Cartesian graph with x coordinates and y coordinates. Okay, so a parametric equation is slightly different. This time x and y are written in terms of a third variable, often t, and it often represents time. The input of a parametric equation is this value t, okay, this parameter, and the output in this case is a pair of coordinates x, y, not just what y is. We can be asked to change from a parametric to a Cartesian. Okay, worth pointing at this venture, we will not be asked to change Cartesian into parametric because there are infinitely many ways of doing that. We could be asked to sketch a parametric equation. We could be asked to model a problem using parametric equations, and there's a few other little bits and bobs that we may be asked to do. But for now, let's have a look at this problem. So it's in parametric form, x in terms of t, y in terms of t, and we've been told some restriction on this value of t. So first job to change into Cartesian, if we're given something in this form, is take this first expression and make t the subject. Now we have something written in terms of t, we can substitute it into y. And then, that's an okay format. Actually, it's a very, very useful format. It looks like it's in completed the square form, which means we know turning points and things like that. But we could also expand it and then collect like terms. So there you have it. We've written it in Cartesian form. The only thing that's left for us to do is find the domain and the range. Now this doesn't change in terms of what it means. So the domain is still x and the range is still y. So we need to use these values of t to find out the restrictions on the domain and on the range. So let's have a look at the domain to begin with. So the domain, okay, so this is lovely and linear. So let's have a look at what happens at the extremities of our restrictions. So that's going to be -2 add 2. So that was our value of t. So that is 0. And then let's have a look at the other side. So 1 add 2, and that is 3. So that tells us that the domain of this Cartesian function is that x must be between 0 and 3. Okay, what about the range? Now, a little bit trickier this because it's a quadratic. So, we're told that t is between -2 and 1. So let's just do a little sketch of what this looks like. It's sort of like that, isn't it? A little quadratic like that. The turning point is there. It goes through the axes there at 3. So what do we have? Well, we have that the smallest possible value is 3. It could be 3. Now this is the more difficult bit. So I need to think about when I substitute these values of t and what is going to give me the maximum value. Okay, so if I chuck in -2 and square it, I get 4, and add 3, 7. So that's actually the largest possible value I could give. So that is my range of this function. This is something that requires a little bit of practice. Okay, example 2. We're told that t is greater than 1. That's the only restriction on t. X is an exponential function. Y is an exponential function as well. Now, we could make t the subject here, but from experience, there's no need to do that here. Because I already have e to the t as the subject here, I can substitute this straight away into y, and it gives me a lovely linear graph. And that's it. It's now in Cartesian form. Now, what happens when t is greater than 1? Well, it means x has got to be greater than e. That's the domain. And the range y has got to be greater than 2e plus 4. And that's it, done. So sometimes when we have exponential functions, it's actually a lot easier and quicker to work with. Okay, third example. So this time we have a logarithmic term, a natural logarithmic term, and the quadratic. So we're going to have to do a little bit of work here, and t is greater than -1. We can hopefully see why that is the case. So let's start off with x. So I'm going to take exponentials of both expressions, and then I'm going to write it like that. So now I in fact have t is the subject, so I can substitute that in. And that's okay to leave it like that. I could expand it, don't need to. But that is now in Cartesian form. Now t is greater than -1. It means that x must be greater than 0, because if I put in t as -1 into that, I get ln 0, which doesn't exist. So therefore x must be greater than 0. And for y, again, if I chuck in -1 into there, it would give me -4. But if I put 0 in there, it would give me -5. So I have to be a little bit careful here. So I know that y has got to be greater than -5, because then obviously it shoots off to infinity. Okay, so remember, watching this does not mean you instantly will get it. It will require a little bit of practice, particularly finding the domain and the range of a Cartesian function. Practice is the key to success, and the more you practice, the better you will become. And obviously, most importantly, finally, amateurs call it genius, masters call it practice.